All right, so just in case people don't even have Rust installed or don't know how, you can go to the rustlang.org website. There's an install tab. It will detect what operating system you're on and show you the easiest method to install it. I believe that Windows users will also have to install the Visual C++ build tools. You can get those from the Visual Studio. You can do it separately too. It's just the easiest way. It's a pretty long install though, but the community edition is free. You don't have to pay anything. So once you get Rust installed, you should have 3 key things available if you open a new command prompt. Rust C should be there, which is the compiler. There's cargo, which is kind of like a build tool. And then Rustup. And Rustup sort of manages your Rust installation. So you can run Rustup update. It'll download the latest versions of the Rust compilers and stuff and assorted tools and install them for you. So it's really handy for keeping up to date. Just every now and then run Rustup update. Everything's up to date. So if you want to start a new project in Rust, one thing you can do is you could just let's make a folder. You could just like fire up Notepad, right? And make a little program. We'll save that as main.rs. And then you can run the Rust compiler. Did it name it text? It did. Let's see. Ooh, I spelled it wrong. All right, so that's the compiler giving me an error. Whoa. All right, so now we've run the compiler. We have an executable file. We can run it. So that's hello world. So that's easy, but that is not the way we normally use Rust. We normally use cargo. So let me delete that folder. Learn Rust. We gotta get out of here. So cargo is kind of like a build tool. One of the things it can do is it can initialize a new project for you. So if we say cargo init learn Rust, right, it'll now make that folder for us. We got to learn Rust. Now we have a bunch of stuff in here. All right, we have a cargo toml, a source folder. We go into the source folder, we see a main.rs. So cargo is sort of set up like a, this would be equivalent to like a solution or project, right, if you're working with C#. And we can use cargo to run this thing or build it, and cargo will take care of figuring out what are the dependencies you need, linking those in, compiling all your files together, right? So you don't have to pass 1,000 arguments to Rust C all the time. So here's our hello world running. All right, so for code editors, you can use any code editor you want. Visual Studio Code is one of the easiest ways to get started with Rust. Just because, for one, it's cross-platform, but also it has a decent extension. It's not perfect, but it gives you somewhat of an IDE-like experience. So if you go to the extensions, the one you want is Rust RLS. And this uses the Rust language server, which is a standard Microsoft came up with to give you things like let you know about errors right in your code and give you autocomplete and stuff like that, and IntelliSense type features. So if you install that, you'll get those things. It's not super great. It's a little bit slow. It's got some things it can't handle. There's an RLS 2.0 in the works, which should be much better. Hopefully that will exist soon. And you can use the Rust language server with other editors as well. VS Code is just the easiest to get going with. All right, so this is our all our stuff over here, right? This is our main.rs inside the source folder. And there's this cargo toml file. That is just like equivalent to a solution file or a project file in Visual Studio. You can list what libraries you're going to need down here under dependencies. That's kind of where when you say cargo build, right? It starts here and figures out what packages you need and stuff like that. And then inside source goes your actual source code. All right, and so from Visual Studio Code, I just use a little built-in terminal, and right, as you type code, you can type cargo run. Another thing you can do is cargo check. What cargo check does, it doesn't actually build the code, but it checks it for errors. So you can see if there's errors and where they are, and it's just faster than doing a full build. And because one of Rust's weaknesses is slow compile times, people like to use cargo check a lot. All right, so we've got a Rust project set up and working. Cargo check's a nice feature. So what is Rust? What's it for? What's the point? So Rust is a language whose main motivations are to be as fast as C or C++, but to be as safe or safer than languages like C#, Java, and Go. And the main reason those languages are safer than C or C++ is that they offer memory safety, and they do it with garbage collection. And memory safety is important because the kind of bugs you get with memory mistakes can be worse than just crashing or getting the wrong answer. Really bad things can happen, like say you have a server that's managing people's credit card info. A memory mistake can end up leaking data about those credit cards to someone who shouldn't see it. Or a memory mistake could allow someone to run arbitrary code of their own choosing on your server and then take it over completely. And memory mistakes can be bugs that are really hard to find. So Rust was born when the people who were developing Firefox, kept having these kinds of problems, and everyone who works on C or C++ code bases has these problems to some degree or another. And they're really bad bugs, right? They affect users in a bad way, and it's really hard to manage. But they couldn't turn to something like Go or C# or Java because it wouldn't be fast enough for a web browser, right? A web browser is doing a lot of stuff. It's got its own language, a compiler in it. It does this pretty complicated rendering. It's got to be fast. Are there any reported of large-scale Rust services apps that have been hacked? I don't know of any. There's no reason that can't happen, right? There's tons of ways to make mistakes besides memory errors. Memory errors is a very common one. So writing a program in Rust does not mean it can't be hacked at all. If Rust gets adopted widely, Rust things will be hacked for sure. There's no doubt. But there is some empirical evidence that it will happen less often. A lot of that is from the pieces of Firefox that are written in Rust have had fewer vulnerabilities of that kind. Like they've already seen some of that. So what Rust does is Rust ensures memory safety at compile time. But there is a catch, and the catch to that is that in order to figure out if your code is memory safe at compile time, is it puts some restrictions on you. There's some things you're not allowed to do in safe Rust that you could in C or C++. And that can be hard to deal with sometimes. Depending on what you're working on, you might never notice those restrictions, or they might drive you crazy. And with experience, you get better at working around it and not running into problems in the first place. And then there's some bonus things that Rust helps with those same restrictions, which is the Rust compiler will not let you write multi-threaded code that has data races. That means that there's different threads trying to read and write to the same bit of memory at the same time. Can't do that, it doesn't work. And Rust will tell you at compile time if that's going to happen, which is another kind of common mistake that's really hard to debug. So that's kind of a bonus you get from these restrictions that give you memory safety. And then Rust has a lot of other features that help you make you less likely to make errors of other kinds. And most of those are actually really nice to work with. So you do get some things that are just nicer to use, and we're gonna see some of those today. So let's get started doing some code. And if there's any questions, just fire away, and I will pause. Okay, so variables. The syntax for making a variable looks something like this. All right, we say let x equals 5, and we get a little warning that we're not actually using x here. It's just a warning, not an error. So let's print it out. So the way you can print out variables in Rust using the println macro, and you know that println is a macro, not a function, because it has this exclamation mark on it. All right, we're not going to talk about macros much tonight. Just know that println is a macro, and that's why there's an exclamation mark. So for any like number of these things you have, you can provide that many variables here, right? And it will print them, which is why it's a macro. It does some magic to make that possible. Right, so we have one variable we're gonna print, so we do one open close parentheses. Right, so we can do something like that. X equals, this will get replaced with x. So let's give it a try. Cargo check says it's good. So we run it and we see x equals 5. Excellent. So you'll notice that we didn't give x a type here. But Rust is not a dynamically typed language. It's not like JavaScript. Right, so you might be familiar with, like in C#, right? You can say var x equals 5, or in C++ you can do auto. So Rust does that too, but it also goes a step further. For instance, we could declare x here, and then on another line say x equals 5, and that still works. So the type inference that Rust does extends beyond just the line you're on. It can look through the entire scope that you're in, so the entire function you're in, or other scope, to figure out what your variable must have been, right? And if we hover here, we see that it's an I32. int32 is what type inference has decided x is. So if you're familiar with like type inference in C or C# or C++, this goes a little bit deeper. If you're familiar with type inference in like Haskell or F#, this doesn't go quite as deep as that, because functions, if your functions take in variables, you have to declare their types there. The type inference won't pass through functions or scopes. Now, if you want to declare your type, because so in Rust, expressions, not values, are typed. I don't know if that's a correct statement. Like, expressions end up as values. And everything's got a type. It's not dynamically typed. But we'll get into everything being expressions soon, which is a nice feature too. So if you do want to define your type, because sometimes the type inference can't figure out what you want it to be, you do it like that. The colon and the type, and you set it equal to the value. All right, so there we're just saying explicitly we want that to be I32. All right. Okay, so structs. So if you're used to classes and structs in other languages, Rust is pretty familiar. There's only structs, right? So we can make a struct like, say, point. Oh, okay, so chat has a good question. If you don't assign a value to x, does it get a default one? So let's try running this. Okay, it says type annotations needed. So let's give it one. So if you don't give x a value, the compiler will not let you compile, right? It tells us use of possibly uninitialized x. So if the compiler can't be sure that you've initialized x, it won't compile. So again, in the theme of safety, which is an important thing in Rust, you can't do that, right? You could do that in C, and I think depending on your compiler options, it's either set to 0 or just undefined. It could be anything. But in Rust, it just won't compile. You have to assign it. Good question. Okay, so up here we've defined a struct called point. So we made a new type called point, and we have two variables. It has an x and it has a y, and they're both F32s. That's pretty much the same as you would expect in Go or Java or C#. Just know that there's only structs. There's not like classes and structs like in C#. Okay, so how would we make a point? One way, you can say let point can use this syntax here. And you could say 1.0, y equals 2.0. And then we have a point. And we can try to print the point. Let's go ahead and try that. And we can't. It says point cannot be formatted with the default formatter. And there's another way you can print a debug print that will sort of go into more detail about the thing you want to print. So we can try that too. But it says point cannot be formatted using that either. And you'll notice you get help, a lot of help from the compiler. The error messages are like pretty verbose. It says the trait debug is not implemented for point, add derive debug, or manually implement debug required by format debug format. So what it's telling you is in order to print a type, the type has to implement a trait. And a trait you can just think of as an interface for now. It's very similar to interfaces in C# or Go and so on. So that it can call that function on the interface to get the string it needs to show on the screen, right? So one way you could do that is you could do it by hand. See, it says manual implement. You could say impl debug, impl debug for point, and then in here you provide the necessary function that, or function or functions that debug needs. But that's a lot of hassle, and you don't have to do that because there is a built-in attribute that can do it for you. Unless your type is bizarre, you can just say derive debug, and it will sort of at compile time insert the code to implement debug for you. Code blue, you say you see nothing. Nothing at all? What do you mean? So an attribute, this is an attribute, and it is associated with whatever type is below it. And what actually happens behind the scenes is that a macro is run on this that adds the implementation for debug. Code blue, I think something might be wrong on your end. You can try refreshing. It's working for other people and working for me. Right, so you can actually, there's a way to, I don't have it handy, but you can actually look at how your code looks after all the macros have run. And if you did, you would see on here, it would say impl debug for point, right, after that macro step. And then it would go ahead and compile it for real. So in the end, what we get is we can now print our struct in a nice way. We see everything. And these attributes can be used for lots of interesting things. We'll see more later. Can you define a default value for a struct? Okay, so good question. So what you can do, Rust does not have constructors built in, but you can just make a constructor, right? So if you want to create methods that are associated with a type, unlike in C# or Java, they don't actually go in here, right? They go outside. So you say impl point, and then inside this is like the implementation for point. You can put whatever functions you want. So you could make one called new, and you could say that is going to return a point, right? And so then in here you could do your default, right? You could say point x y. And then here you can say let point equal point new. Right? And so because this function doesn't take in an instance of itself or this, and we'll get to that later, it's like a static method in other languages. And to call static methods, you use the type name, : and then the function name. Right? So that'll give us a, gotta save it. That'll give us a point with this, the value assigned in new. Do you have to explicit lifetime of the thing in the constructor? We're not really going to get into lifetimes tonight, but I haven't done any explicit lifetime things with this, right? So none of this stuff we've done so far is going to be on the heap. It's all stack allocated, so everything just pops off the stack as you leave functions and stuff, right? So this function returns a value point that ends up here, for instance. All right, let's see. So let's get into some of the weird memory stuff. Oh, how do you return? Good question. So in Rust, if you don't put a semicolon at the end, you get an implicit return, right? So if I add a semicolon here, now there's an error because it's expecting me to return a point and I'm not returning anything. If I don't have a semicolon on the last line, that's an explicit return. You can also type return if you want to. You can do it either way. Okay, so let's get into maybe the most unique feature of Rust, which is the borrow checker and what it does. So yeah, let's say it's a point equals point new, right? And then let's say we want to make a copy of that, right? We want another one that's the same, so we'll just do this. And then let's print both of them, make sure they're the same like we expect. Okay, and we get an error here. Now, if you haven't done Rust before, this error will be really, really strange. You'll never have seen anything like it. It says borrow of moved value point. Move occurs because point has type point, which does not implement the copy trait. That's important. That's just like we didn't implement the debug trait before. And the value is moved here. And the value is borrowed here after the move. So what does all that nomenclature mean? So what happens right here, because point does not implement the copy trait, we don't make a copy of point and assign that equal to point 2. And point is not a reference. This is an actual value, right? It's not like a class in C#. Everything that's a class in C# is a reference, right? In Go, you can have references or values at will. All right, so this is a value. So we can't copy it, and it's not a reference. So what happens? What happens is point moves, right? Like point becomes point 2. I'll see you later, 3A, 2L. I'll put this up on YouTube later so you can tune in. Point becomes point 2, and point disappears. Or you can think of it as point 2 consumes point. All right, so we don't have a point anymore, and we're trying to print it. So we can't. That's what's going on. And that's one of the key things that allows Rust to ensure memory safety. So what are some options here? Like, what if we really wanted to do this? One option is you can say, you can use a reference. Right, so we can use the and sign to make a reference. And now point 2 just points to the same data that is in point. Right, and Rust will let you do that all you want. You can make as many references to some data as you like. Right, and we can use them all. Print them all out. They're all the same because they're all pointing to the same thing. Right, if we change, if we were to change point here, it'd be reflected in all of them. So let's actually try to do that. So let's change part of point. So let's say point.x equals 2. What's going to happen? Oh, okay. So we can't. Here it says, consider changing this to be mutable, cannot assign. So by default, any variables you create in Rust are immutable. It means you can't change them after they've been created. If you want to be able to change them, you add this in front of it, mute for mutable. So if we make point mutable, sorry, I gotta move this up here for now. If we make point immutable, then we can change it. And we see how point 2 and point 3 also have the 2 because they're pointing to the same structure. All right. So what if I wanted to change point 2? All right, so we see we get an error there. And we can say here, point 2 is an and reference, so the data it refers to cannot be written. All right, so when you use the and operator, like that, it is an immutable reference. It means you can read that data all you want, but you can't write to it. And that's why Rust will let you make as many of those as you want. It's safe for hundreds of things to point to the same data and read from it. But as soon as multiple things can write to the same data, it's no longer safe. It's no longer safe for the way that Rust analyzes your program. So for example, we could do let's try a simpler example first. Do that. Make this a little bit too. Okay. So yeah, if we make a mutable value a, then we can make one mutable reference to a, right? And then we can say b equals 2, or we have to dereference. So to dereference the value so that we can actually change what b is, you use the star. And gets you the reference, star gets you back the value. Didn't save it. All right, so that's good. But if you want to make a second mutable reference to a, oh, you know what? Okay, so this is a good example. This is why Rust can be confusing. All right, so this is working. Let me try something real quick. So this is working because of the copy trait. So this can be confusing because you can think Rust is a normal language when it isn't. So let me find a better example. Just a second, I had one up. Let's try this one. So, point 1, point new. So this should be fine. Okay, we can print point 2, which is a mutable reference to point 1. Okay, so yeah, this is the error you get that shows you the limit that Rust puts on you on only being allowed to have one mutable reference to a thing at a time. Right, so as soon as you get to the second one, you say we got the first mutable borrow here, second mutable borrow occurs here, and the first borrow is later used here. Right, so if we didn't use point 2, this would be okay. It's okay because this wasn't used after it lost. Right, once we get the second mutable borrow, the previous one is gone. That's why the previous example worked, because we didn't use the first borrow. So this is the super weird part. So any questions about this? We'll see some more examples later, as we're going to start sending these things to functions. Okay, so that Joker's Wild asks why. With that limitation of only being allowed to have one mutable reference to any bit of data at a time, Rust is able to guarantee, it's basically able to do what garbage collection does at compile time. If you don't have that restriction, it's just not possible to do that. At least outside of like very simple programs. You can't do the static analysis without that limitation. Yeah, and that same rule prevents you from having data races when you multi-thread. So that's a bonus you get. Right, and the simplest thing that you can think of where this becomes a big problem is something like a doubly linked list, right, where any node can write to the node before or after it. This rule makes it difficult to do that. So like making a doubly linked list in Rust is tricky. You can do it. And then if you do run into something that's fundamentally impossible to do without multiple immutable references, you can use unsafe Rust. And you can make an unsafe block, and then you can do what you want. But in safe Rust, you can't have two immutable references at the same time. All right, so let's move on. Let's do a let's extend our implementation of point. We're going to make a function called divide, and it's going to take a point in, and it's going to take a value called v, and it's going to return a new point. And the way this will work is we will say return a new point where x is the old point divided by v, and y is the old point's y divided by v. Pretty straightforward. Okay, and let's make our new actually take in an x and a y. We're not going to have a default. Call it 2.0 and 4.0. All right, we'll just call this point now. So Brain asks if the constructors need to have the X part. So there are times when they don't. If you do things in order like that, you can shortcut. If they're out of order, you need to name them. And I might even need, like, I don't know if you can do this or not. Let's see. No. So I think it has to, like, if it has the same name and is the same order, then you can do the shortcut. All right, so let's, we've got our point. Let's divide it. So we'll call point divide old point and divide by 2. Sorry, Code Blue, I don't know why my stream in particular would not work on Android. I'll have this up on YouTube, so you could tune in then. All right, so let's print out the divided result. And we get 1 and 2. Okay, that's pretty straightforward. But what if we printed out point here? All right, so remember before when we talked about moves, this happens when you call functions as well. All right, so our point does not implement the copy trait, like it says here. So when we pass it to the divide function, it's not making a copy of point, and we're not passing it a reference to point. So what ends up happening is point is moved into the divide function. And then when the divide function is done, it's popped off the stack of divide and it's gone. Right? So after we call divide, we don't have point anymore. It's gone. So what can we do? If we wanted to keep our point around, what are our options? One option is this could take a reference to a point. And we're not changing this point, so it doesn't need to be mutable. We could make it mutable, but we don't need to here. And then instead of passing point, we pass a reference to point. All right, so now we're just passing the memory address of this to here. All right, that'll work fine. We have to save it, and it'll work fine. Brain, so yes, functions will own the arguments they're passed unless they implement the copy trait. Or I guess the functions will always own the parameters they're passed. There may also be another copy left behind, but the function will always own it. That's correct. Okay, so now that we're passing a reference, we can get our 2, 4, and our 1 and 2, and so on. So the other option, just like debug, right? We could implement copy for point, and then provide the necessary methods to make a copy of a point. But again, that's usually a trivial thing to do. So you can usually use derive, just like we did with debug. So we can add a couple here. Copy and clone. I won't get into the difference too much, other than copy tends to be like a shallow copy, clone is like a deep copy, which would be necessary on more complicated types. Copy is kind of like cheap and easy to do. Clone might not be cheap and easy. So Brain asks, why does passing the references not error? Yeah, and is an immutable, so it would not let me modify point. If I tried to modify point, it would. I'll get a red line. Yeah, red line. Can't do it. Okay, so now we implement copy and clone. So that means we could go back to not passing a reference, and it'll be okay. All right, so now we're passing a copy of point. And a good tip when you're starting with Rust and you can't get something to work because of borrow checker stuff that you can't get your head around, unless your type is really huge, just implement copy. Like if everything implements copy, things kind of act like normal, like a normal language. It works fine. All right, and computers can copy a really huge amount of contiguous memory really fast, so this is usually fine. But of course, a reference will be smaller than most structs. That'll just be, 64 bits on my computer anyway. Okay. Let's get more into these impls, right? So this really isn't acting like a method yet. This is still just a static method. We're having to call point divide. What if I wanted to do it like this? If I wanted to say point.divide, right? Like we expect in our object-oriented languages. The way you do that in Rust is you say that the function takes in self. And then we replace point with self. Right, so self just refers to our self. This is like this in C#, right? So that lets us access the things in our struct. Right, so now this is completely equivalent to what we did before, except you can use method syntax. Does the same thing. All right, what else? Type inference, moves, borrows. Introduce self. Okay. Okay, so self can also be a move or a reference. So like if we get rid of the copy and clone here, we get the old error again about moving. And this is sometimes less obvious. You're like, why is point being moved? It's because it's equivalent to calling divide and passing point into it, right? We've just moved the point over to the left. And self is not a reference, and we don't implement copy anymore, so it's getting moved. Point gets moved into divide, right? So you can either make that a reference, you can do and self, or and mute self if you need to mutate yourself, or implement copy. That Joker's Wild asks, is using self considered a best practice? It certainly is less typing than having to type the type name, then colon, then divide, then pass the thing, right? So yeah, I think it's the normal thing people do, like when it makes sense. When you're passing an instance of self in, that's usually what people do. But you can do what you want. Doesn't matter. Like it compiles to the same thing, I think. Copy has to go with clone. You got to do both. Brain asks, so you can only use point.foo syntax if you use the self stuff. Yes, that's correct. That's basically what tells you you're making a regular method instead of a static method. To refer to other languages nomenclature. Okay, now stuff that I think is really cool. Okay, so divide is a function that can fail, right? If you pass in a 0, this division will result in not a number or throw an exception, like bad stuff can happen, right? So divide is a function that can fail. So how can we represent that in our function? So the way a lot of languages would handle this is you might do something like, right, if v equals 0, then maybe you return null, right? Something like that. But Rust doesn't have a null. There are no nulls. So you can't return null. The way you would do it in Go is you might do something like if v equals 0, return, some default point, or actually I guess you'd return like nil for the point, and then you return some error, right? And this would have a tuple, multiple return values, right? And you could do that. You could do that same kind of thing in Rust. You can have multiple return values. You could panic. You could make the program crash, but we don't want to be that extreme. What you can do is we can use enums. So enums in Rust are very special. They are not like enums in most other languages. So we're going to make an enum called good, no good. And it's going to have two cases, good, just good, or no good. So far that doesn't seem that special. Looks like enums in any other language. The cool thing about enums in Rust is they can contain data. So we can say good is going to contain an F32. It's going to contain one 32-bit float. And no good won't contain anything, for now anyway. Okay, so what can we do with this? Well, we can say, actually this will contain a point, not an F32. It's going to contain a point. All right, so now we can make our divide function return a good, no good, instead of a point. All right, so now we're getting an error, returning the wrong thing. So what we can say here is if v equals 0.0, and you don't need parens with if statements in Rust. You can save yourself that typing. Then we're going to return no good, right? Else we're going to turn good with a point in it. Why aren't these matching up the way I want? There we go. All right, so if equals 0, return no good. Otherwise, we return good with the point inside, right? That's the data that good can store. So how do we use it, right? So, oh, another thing to notice is if statements are expressions in Rust, right? So this has no semicolon, so it's a return value, and this has no colon, so it's a return value. So the whole if statement ends up a value, right? Either this or this. And you can do stuff like this. You can say let equals an if statement, which is really, really handy. So it's like instead of like in a lot of languages, you would say something like var x equals 0, if foo, right, then x equals 2, else x equals 3, right? You don't ever have to have that invalid state. You just say let x equals if blah, 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 blah. I really like that. That's really handy. All right, that's what we're doing here. Okay, so we can't print divided anymore because now it's this good, no good thing. So what do we do? So there's a thing called a match statement, which is really similar to a switch statement in other languages. So we're going to match on divided. And we're going to say, okay, if it's a good, no good, good, or let's say it's no good first. What do we do? Maybe now we can panic, right? Like, we don't know what to do with this. Divide by 0. And panic is a special macro that will end your program and print the string. Brain's really excited about panicking. All right, but if it is good, we want to get that value out, right? There's a point in there. How do we get it out? You just put a paren here and give it any name you want, right? And then we just want to return that. So we're just do point, no semicolon, and that will return it. And then we can say, do it like that. We can say this is like divided maybe, right? Because we don't know if it's divided. And put a semicolon here. Oh. Put the maybe in the wrong place. Okay, so again, this match statement is also an expression, right? It's going to return either, in this case, nothing, the program will terminate, or it returns a point. So we can say let divided equals this whole match statement. All right, and then we can print divided. It should look just like it did before, divided by 2. But if we pass in a 0, we panic, right? Thread main panic with divide by 0. There's our message. Can I collapse the match into the upper line as well, like you did? Yeah, I mean, you can arrange it however you want. You can put it up there. There is a built-in tool in Cargo called Format, which will automatically apply like the official coding standards to your code. And this actually, like, I don't think that's official. It just doesn't care. So I could do it like that too. And I really like that kind of thing because I don't care that much about formatting, so I like to just use the automated tools. And you can change settings for this. If there's some aspect of it you hate, you can go change the setting. It'll do it differently. Okay, so good, no good lets us have a function that can return something correct or not, right? It can fail or not. And it makes it so it's impossible for us to screw up, right? So if we forget to check, let's say we forgot to check, right? We forget to check the no good case. What happens? We get an error, right? The compiler actually looks to see that you've checked every possible case in your enum, right? So if someone later along comes along and says, well, you know, there's a third type, it's okay, but not great. Maybe it's an inaccurate division, right? You're gonna get an error, right? It's impossible to forget to update your match statements that go with this, right? So what's really nice about this is you'll never get a null pointer exception unless you explicitly like decide to, like I did here. You'll never get one because you forgot. The compiler won't let you forget. All right. So this is a really handy tool, right? This good no good thing. Oh, here's a so you don't have intermediate divided. Oh, okay. So yeah, Brain is asking, can you just do this? Wait. He's asking, can you do this? And the answer is yes, absolutely. And that is what I would do normally. So yes, that works fine. But we're panicking because we gave it a 0. Yep. Okay. So this good no good is really handy. But it kind of stinks that it only works for this point. What if we wanted to use it for other types besides points? So Rust has generics. So you can say this function is going to be generic over whatever type you want, right? Over any type T. And then good won't contain a point, it will contain a T. And then this function, we need to say what kind of good no good are we going to return? It's going to be a good no good with a point in it. All right, so now we've got the same program, except now we can use this good no good for anything, right? Anything when I put something in, we're good to go. And there's no runtime penalty for using generics. So like when you compile the program, every type that you use with this enum, it creates, like it makes a copy for every type you use it with. So each code path gets its own, its own code. It's exactly the same as if you wrote it the other way. All right? So that's still really handy, but it's kind of stupid that you like have to make this, right? It does not increase the size of the struct. So like in this case, I'm only using good no good with one thing, a point. So when I compile this, it's probably like exactly the same code as if I just had a point here. Now if I used it twice, then there would be two structs. There'd be good no good with points, and then if I used it with an int, then there'd be another good no good with an int. So like the data of my program would have two copies of it, but each individual copy would be the same size. Yes, monomorphization is what that's called, I believe. Okay, so we don't actually have to use good no good. Rust has two things built in that are the same idea. Option is basically exactly what we made. And with option, you don't have to use the longer syntax. You can just say none or some. All right, so options either have some value that's generic. In this case, we're going to use a point. So they're either none or they're some. All right, and then here, that's the none case. That's the sum case. Right? So that is a lot simpler. You don't have to build your own thing. It's all built in. Right? So option is basically the replacement for null in Rust. And then there is a similar type called result, and it's got two generic parameters. One is what's going to be in the OK case, and the other is what kind of type you're going to have in the error case. So in this case, I would return an error with, an error message, because I said it was a string, so I put a string inside. Or it's OK and has a point. Right, and so then here we would say error, and then extract the message, and we can just print the message. And here we would say OK, and we got the point. Right? So that is how you do errors in Rust. You return a result type. Now this is similar in concept to what Go does by having a tuple with two return values, except that you can't screw up and forget to check the error value. Right? It forces you to check it, because if you don't, the compiler will complain about the match statement. And it's similar in a way to exceptions. Right? Any function in C#, for instance, that can throw an exception can either return the value or it can return an exception. Right? The difference is that exceptions will automatically bubble up to any function that doesn't, through any function that doesn't catch them, whereas results do not. You'd have to bubble it up manually, although there are some shortcut operators to do that with very little typing, which we won't get into. Is exception handling efficient? Well, Rust doesn't have exceptions. I don't have an opinion on how efficient exception handling is in languages that have it. Some people get really worked up about it, but I haven't ever worked in like the AAA. Yeah, like this is just an enum. So the way that enums work, it's actually kind of a good question. So if we had a result that we built ourselves, now we have OK with T in it and an error with an E in it, right? And these can be any types. So let's say that it was an I32 and a, I don't know, maybe some float 64 error code, right? Just make this not generic so it's more clear. All right, so this is a type that can be one thing or another. So how is it stored in memory? So basically what happens is these overlap each other, right? So the size of result has to be big enough to hold the single biggest thing in it, right? So this would be 64 bits, always, right? And then if you're an OK result, you only use the first 32 bits of it. And if you're an error result, you use all 64 bits. There are some exceptions to that, like with the option type, right? If we were defining option ourselves, right? You would think that there has to be a little bit of data used up to indicate whether there is some or none on top of whatever sum is storing. But the Rust compiler is really clever, and there's lots and lots of cases where it could compile away that size and like make the overhead disappear. So enums are pretty efficient. If you're making one on your own, right? If you had, right, and then like case 3, or case, you know, if you were doing something like that, you might want to consider a different solution because every enum is going to have the huge data, enough space for the huge data, even though most of the time it won't be using it. So that is something to keep in mind. So yeah, options and results are things that I feel like are very, very useful. They help prevent errors and they're handy, they're nice to work with. So there are no nulls in Rust, there are no null pointer exceptions. Enum, yeah, an enum is its own data type. So like you can pass them around. It is just like a struct. So like if you're familiar with C# or C++, there's a concept of unions. Right, you can do something like that. These overlap. Like X and Y are in the same space in memory. And in those languages, it's just your job to make sure you use the right one. Right? If this were an I32, right? It's your job to keep track of which one the union's actually storing at any given time. And enum's the same way. Right? The data overlaps. But the compiler won't let you use the wrong one. It keeps track of it. But it is a data type. And you can pass them, copy them, you can make impls. You can make an impl for your enum. Right? So like good, no good, good, no good. Right? You can have methods on that too. I spelled that totally wrong. Right? So you can make a function new that returns 1, right? You can do all the same things. I hope that answers the question. Okay, 2 more quick things. Enums can be used as an alternative to inheritance. Rust does not have inheritance. So you could do something like this, for instance. Say a classic example you see a lot. And by the way, enums in Rust are the same thing as sum types or variants or discriminated unions. Lots of languages, mostly functional languages, have these, and they all have different names for them. So if you hear those names, they're talking about the same thing. So we could have a circle, which has some radius, or we could have a square, which has some side length, or we could have a rectangle, which has 2 side lengths, right? And then we could do an impl for shape, and we could have a function that computes the area. It takes in a self, and then returns some area. And then we can say match self, and we say, okay, if we're a circle, all right, then we get our radius out, and then our area is, what is it? Pi r squared, is that right? And then if we're a square with our length, then it's just length times length. And if we're a rectangle with our length and our width, then it's length times width. Oh, I did the wrong arrows here. Oh, you have to do it. You have to do the full line. I forget that a lot. Not all languages make you do it that way. All right, so then if you wanted to use it, go down here. We can say let shape equals shape circle 3.0. And then we can just call shape.area. Oh, we're inside impl point. Oops. Undo. Leave that in there. And then let's print line area. There you go. So using enums that way, a lot of things that people would turn to, like making a shape class and then a circle subclass and then a square subclass, then a rectangle subclass, and then each of those would have their own area function, and each of those would have their own data and so on. You can just do an enum and a function with a match statement. It's way less code. If it's in Java, it's actually way less files, since you have to have a file, I think, for every class. So it can be a really handy way for like some of the things you would turn to inheritance for. Enums can be much, much more concise. Enums and matching are one answer to the inheritance way of coding. The other answer is something called traits, which, what's a good one I can, so yeah, so let's say that you wanted to do area, you wanted to expose some sort of interface that could compute area on more things than just shapes. Hey, DizzerDev. I hope this has been helpful. So traits are Rust's form of interfaces, right? So you can define a trait. All right, so we'll call a trait has area. And inside of a trait, you basically just provide like function definitions. You don't actually provide the implementation normally. So you can say area. All right, so now we have a trait called has area. Now, if we want to make shape implement that trait, if we want to make it satisfy that trait, we would do it like this. We would say impl has area for shape. Right? That means, okay, we're gonna make shape satisfy this trait, and you have to provide this function. Right? And what that'll let you do is if you come up with some other type, right, like struct garden, right, and maybe it's got some polygonal shape and then you want to have it also be and has a has area, then you can impl has area for garden too. And then that can let you in the end have something like a list of has area that has various things in it that aren't actually the same type. That's how you do that kind of thing. Would learning Rust be overkill for back-end web development? It really just depends. Like if your particular web backend needs to be really, really fast or has really, really strict safety and correctness requirements, then Rust might be something that makes sense. I don't think Rust backend web development is a common, like it's not something commonly used for it. It might be more common that like one piece of the backend might be in Rust. You know, like I know of a company that does like power grid simulations, and they're doing a lot of their math in Rust, but probably not their whole website is in Rust. Yeah, so another interesting thing about WebAssembly is because it uses LLVM to compile itself, LLVM can also compile to WebAssembly, and Rust has made a concerted effort to be a good language to compile to WebAssembly. The problem currently for any garbage collected language, if they want to compile to WebAssembly, they also have to include their runtime. They have to include their garbage collector as part of the payload, because WebAssembly doesn't have one built in that they can use. It may in the future, but right now it doesn't. So Rust doesn't need a garbage collector, so it's easy for it to compile to WebAssembly. So you can replace, you know, almost all of your JavaScript with Rust that compiles to WebAssembly, and it'll startup time is faster and performance is faster as well, even after it's loaded. So that's one advantage of it in the web space. If you have, you know, a lot of computation or big programs running on the client, Rust can make it perform better by compiling to WebAssembly. I've never done any of that myself, so I don't have like tips on how to get into it. All right, that's basically all I wanted to cover tonight. Does anyone have any questions or thoughts? Sure. So let's see. I'm trying to think of an example that is meaningful but not too complicated. Let's see. Let's see if it'll let us do this. Trying to remember how this works. I did it once recently in the image evolver stream, but it's weird. Yeah, I'm not going to be able to throw a good example together right now, but like a common thing people want to be able to do is like have, like, you know, like in C# you might have like a list of things that implement some interface, and they're not all actually the same. And you can do that in Rust. So like in Rust, to make the equivalent of list T in C# or vector in C++ is vec. So you can do like let shapes equals vec new. All right, that makes a new vector. Doesn't know what type it is yet, but it's going to find out through type inference. We're going to say shapes dot push shape. So that's going to add a shape to the list, and it's actually an array behind the scenes, not a linked list. We need to make it mutable. We can do things to it, and then we can say like shape.0.area or shapes. Oh, area is taken. Let's take a reference. Right, so now we're adding that to a list, and so it's possible. It takes some strangeness I'm not familiar with, but you can have multiple things that implement has area go into this vector, and it ends up being indirect because like by default in memory this will actually have shape contiguous in memory. If you want to put things that implement has area in there but aren't all the same type, it can't do that anymore. So it ends up being, you know, pointer to has area, pointer to has area, and then the has area things are all on the heap somewhere. Saw your recent tweet on saving a bunch of dependencies by doing some simple multi-threading. So I'm actually still using Rayon. What I'm not using is Tokyo to do async IO. And yes, I will go over the threading I did. It was pretty simple. Yes, I was also having trouble understanding closures and ownership with threads. It gets weird fast, but it also prevents data races. So that's a benefit. All right, that's it for tonight, everybody. I hope it was helpful. See you guys later.